T in the curve is a DNN, and you can see that the tagging efficiency for this Higgs-to-BB signal is greatly improved by switching from sort of a more traditional machine learning algorithm like a BDT to a DNN. And machine learning has all sorts of advantages. It provides sort of the ability to analyze maybe really complex problems in a very sort of straightforward and regimented way. And as you can see here, provides very good performance even for sort of what we would think of as very difficult tasks. One of the problems here is that the networks that we use can become very large, and very large networks means very long inference times. So the plot on the right here is a whole array of different image classification networks. The size of the dot is basically the size of the network in terms of number of weights. The x-axis is the number of operations required to run through the network, and then the y-axis is how accurate these networks are in identifying images. So you can see that there's some sort of correlation between how many operations you do and how accurate you are. And some of these dots can be really large. So some of these dots are hundreds of millions of weights or parameters, which is obviously a lot of operations to do. Physics, I will say that physics sort of sits in the upper left corner of this plot. So I have one of the biggest networks that's used, at least in CMS, is called DeepAK8, which is used for top tagging, and that sort of sits at the top left corner, and it's a very small dot that I won't even bother drawing because it doesn't really compare to these giant image classification networks. But that doesn't mean that it doesn't have a lot of weights and doesn't take a long time to compute. So the point still stands even if we're not as huge as some of these more conventional networks. And I will say that some of these more conventional networks have started to be investigated or attempted to be adapted even for sort of physics-targeted problems. Okay, and just sort of to make sure that we're all on the same page, I'd like to sort of go over in a very sort of straightforward view what a neural network is, or at least what I'm talking about. So for most of the talk today, I'll focus on MLPs, or fully connected layers. I won't really delve into CONVs, although they are supported by the tool. But suffice it to say, in sort of the most simplistic view of a neural network, I have some set of inputs that I encode in some input vector x1 on the left here. And then using a weight matrix W, a bias vector B, and then some sort of activation function, I can transform my input vector x1 into some next sort of intermediate vector xm in this case, using the formula that you see in the right here. And this then takes me from x1 to xm, and I can repeat this process as many times as I want, sort of calculating further and further layers until I have a final layer that provides some set of outputs that I want for my network. And this is the sort of the most simple way to think about what a network is. It's a fairly simple sort of setup here. It's just the scale of these basically then allows you to do all sorts of very complicated things. And indeed, you can sort of see fairly trivially that the size of the network basically scales like n squared. So if I have more nodes or I have more layers, the size of this network can get quite large quite fast. So I sort of reproduce this plot that I showed before. One of these giant dots that you see here is an image classification network called VGG16, and this is this whole architecture of it that I'm showing here with all these different layers. This one in particular, this VGG16 network, has hundreds of millions of parameters, tons and tons of these different layers. So these things can get very complicated very quickly. And this is something that we have to contend with if we want to get answers out of these networks. Okay, so that's sort of a general overview of machine learning. I'd like to talk about machine learning and its use in CMS here. So, machine learning, and I've sort of divided up the CMS data processing into sort of different stages. So at the far left, we have the data coming out of the detector. We have collisions every 25 nanoseconds, so we have 40 megahertz data frequency coming out. And this gets sent into what's called the level 1 trigger. This is implemented in hardware, in FPGAs in this case. and has to run in order microseconds. And this is a really hard latency, so the computations have to be done in this time. Because things have to be done so quickly here, the selection that gets done in the level 1 trigger is typically quite coarse, although we have used, or we do use a BDT for mu1 PT assignment. We have to do this in a sort of a very FPGA way. It's not, the BDT isn't computed fully, and I'll actually talk about this in some later slides. The next level, the level 1 trigger then passes 100 kilohertz of data to what's called the high-level trigger, the HLT. And this then runs completely in software on CPUs. The latency is much longer than in the level 1 trigger, so we have order 100 milliseconds, and this latency is no longer hard. So events can take longer or shorter depending on how complex they are. And because we have a lot longer, and because we're running on CPUs in the high-level trigger, we can use some more complex algorithms. And so in the past, we have used both BDTs and DNNs here in order to help make selections. And then finally, the high-level trigger outputs 1 kilohertz of data sort of to offline processing, obviously here running on CPUs. And this then, you can take more than a second to reconstruct the data. You can do the full event reconstruction, and this is where the bulk of the machine learning usage in CMS has been done in the past, maybe for obvious reasons here. The hardware is designed for it, and the the time that you can take to do this is apt for the task. But what I would like to argue today is that just because we have used machine learning successfully offline and we haven't used it in the trigger sort of extensively doesn't mean that there's not a huge potential to improve physics performance by using DNNs in the trigger. The main sort of hurdle to this, the main hurdle to implementing a DNN in the trigger is the inference latency. So obviously if we want an algorithm to run in the high-level trigger, we have to make sure that it runs in order microsecond timescales. For the HLT, we need to make sure it runs in millisecond timescales. Now for L1, this means we have to use FPGAs. We don't sort of get to choose. But for HLT, we can choose, and I'll come to this a little bit later. And so the question that I'll talk about then is how can we do the neural network inference that we want to do in the trigger? How can we do that quickly on an FPGA? And sort of, to answer this, then I think we need to go over a little bit of what an FPGA is, in case people aren't aware. So, FPGA stands for Field Programmable Gate Array, and again, these are common solutions that have been used for a fairly long time to do fast computing. They differ from maybe other hardware, similar hardware, in that you can reprogram FPGAs for different target needs fairly easily, and this is obviously very appealing if you're talking about an experiment, ours where you might want to change the way that reconstruction is done or things like that. At its core, an FPGA has sort of 4 main building blocks. The first is called a DSP, or a multiplier unit, and this basically does the arithmetic that you'd like to do, so multiplication and addition, basically. Is everything okay? It's Cern. I just want to make sure that...
Yeah, sorry, don't wait for us. We're setting up the room finally.
Okay. Yeah, so DSPs do the arithmetic. Lookup tables, or LUTs as I'll call them, are basically a way to implement logic. Flip-flops are basically a way to store data in registers on the chip. And then block RAMs are sort of much larger scale memory that act a lot like, more like memory that we're used to in conventional computers. And basically what happens is that you wire the algorithm that you want to run on the FPGA onto the chip. So it doesn't, it's not like a conventional CPU or anything like that. And because the algorithms are sort of wired into the connections on the chip, that means you can run these at extremely high frequencies. So you can run FPGAs with clock cycles of hundreds of megahertz. and obviously if you do the computation, that means you can get outputs from an FPGA in order nanoseconds. And so these are obviously something that we can use to sort of speed up computations. As I mentioned, you traditionally have to program FPGAs in languages like Verilog or VHDL, and these are very low-level hardware languages. They don't work the same sort of, at least in sort of thought process as conventional programming languages that we may be used to. And this is sort of a pretty big barrier to using them. But it is possible, and it has become sort of more possible recently, to translate C, untimed C, into Verilog VHDL using what's called high-level synthesis tools. And to give you an idea of how big these FPGAs are, I have sort of two main FPGAs. The one on the left, a Vertex 7, is one that we currently use in the CMS Trigger. The one on the right, a Vertex UltraScale Plus, is something that we will use in the future. And you can see that a traditional one of these FPGAs, and these are relatively powerful, has thousands of multipliers, has order maybe millions of LUTs and flip-flops, and you get some sort of tens of megabits of VRAM. So this is sort of the scale of the computing resources on these chips that we're talking about. Okay, so then how do we, coming back to this question, how do we actually do inference on an FPGA? And I sort of showed this picture that I showed before, and I would argue that doing inference on an FPGA is actually extremely intuitive. So we have this formula that I showed earlier that takes us from one input vector to the following layer. And as I mentioned, a multiplier unit does multiplication and addition. And as it turns out, exactly what we need to do in order to compute the following layer from the previous one is to do a multiplication by a weight and add a bias vector. So we can do this exact computation in a multiplier unit. And indeed, we can do, if our chip, like a VU9P, has 6,000 DSPs, that means we can do 6,000 parallel multiplications and additions. The number of parallel computations that you can do is basically just the number of multiplication units. So this is basically perfect for us, right? We can do as many parallel operations as we can fit into the chip. We don't have to wait to compute each one successively in serial. The activation function and the weights and the biases even can be encoded in the flip-flops and the VRAM and the LUTs. And so all these things then, all the components that we need to compute inference on an FPGA, we already have on the chip. And actually they map quite well indeed. And what that means then is basically that every single clock cycle on an FPGA, I can compute every single operation I need to move from one layer to the next, and I can do them all simultaneously in that clock cycle. So if I have 5 layers in my network, I can do every single computation from start to finish in 5 clock cycles, or 4. And so this is actually, this is really powerful. This lets us do very complicated things, or lots of things all at once, which is really nice. And indeed, HLS4ML, which is this package that I mentioned, is basically a software tool that creates these HLS, or these C implementations of neural networks. So I have a link to the Git there if you'd like to try it out. And it supports all sorts of most common layer architectures and model softwares like Keras, TensorFlow, PyTorch, things like that. And the output then, we've designed it to be highly customizable so that you can sort of map it to different size and latency needs depending on the actual system that you're using. And the workflow is also designed to be simple so that you can sort of quickly prototype, quickly test things out, and sort of use it like that. So how does this work? How complicated or simple is this? This configuration file that I've shown here, and this is in particular for a model that's been encoded with Keras, is basically all you need to run HLS4ML. So you basically tell it information about what the network looks like and what the weights are in terms of these JSON and the H5 files. You tell it what Xilinx or what FPGA you're using. You tell it how fast you want the clock to go. And then there's 2 main customization options at the bottom here, the reuse factor and the default precision. And these I'll talk about in the following slides to sort of explain what I mean when I talk about these things. But once you have this configuration file, all you do is you just run the command that I printed at the bottom there, and this produces completely a functional HLS project for you that will do, or that can be implemented to do inference, which is sort of a really fantastic way to go very quickly from Keras into some sort of FPGA implementation. Okay, so the first one of these customization options that I'd like to talk about is the reuse factor. So let's consider, in this case, a very sort of simple network here. So I have 2 layers. I have 2 nodes in each layer. And that means if I want to go from layer 1 to layer 2, there's 4 multiplications that need to get done. There's the green, the blue, the red, and the purple one. If I have a reuse of 1, this is essentially fully parallel, and this means I'm using 1 DSP to do each multiplication. So that means I need 4 multiplications or 4 DSPs to do each one of these things, and that means I get to do all the computations all at once in 1 clock cycle. And so then this is what I was talking about earlier, where I can move from each layer to the following one every single clock cycle, and the latency that I have for my network is therefore the number of layers that I have in the network. This is great if your FPGA is of infinite size and you'd like to do things quickly, but FPGAs are limited in size sometimes, and so in principle there's reasons that we might want to sort of shrink how many DSPs we use. And so the reuse, increasing the reuse basically increases how many times each multiplier does one of these multiplications per layer. So in an example of a reuse of 2 here, you can see that the blue and the green multiplications go into 1 multiplier unit, and the purple and the red ones go into another one. And this obviously means that it takes longer to move from 1 layer to the next, but it takes half as many DSPs, and obviously then there's a full sort of range of reuse factors you can do, all the way up to having a reuse that's equal to the number of weights or the number of multiplications I need to do at the top with a reuse of 4, where I just have 1 multiplier unit that's used and I send each multiplication through it every single clock cycle. And this reuse therefore basically lets you sort of trade latency for resource usage and sort of shift those around to match the needs of whatever sort of implementation you're using. The other customization option that I mentioned was this precision. So, I think we're used to thinking about floating point precision a lot, but FPGAs are not, really designed to do floating point operations. And so HLS4ML uses fixed point classes for all its arithmetic and computations. And so, I have some number here, and I get basically I assign some number of bits to be integer bits, in this case 4, and I assign some number of bits to be fractional bits, in this case 10. And this basically, specifies how the range of numbers I can encode on my FPGA. So, perhaps I don't need to encode numbers larger than 16, and that means I don't need more than 4 bits for my integer bits, and same thing can be said for fractional. So you're allowed to, in the configuration file, you can adjust this precision to basically tune it for whatever your particular model or your particular inference needs in order to be successful and to be precise. And so now with these 2 customization options, I like to show this workflow diagram here. So, the sort of standard workflow that I would say you use with HLS4ML is you have some model that you've designed with standard software tools. You then pass the network architecture and the weights along with sort of configuration parameters like the reuse and the precision to this HLS4ML software, and that creates an HLS project. And because this is such a sort of a straightforward and simple procedure to take a model and produce an HLS project, it's really easy to do all sorts of development and prototyping and sort of tune the configuration for HLS and for your inference to be exactly what you want it to be, and to do this very easily. And then once you have a project that sort of meets all the specifications that you're interested in, then you can go about interfacing the HLS code that HLS4ML produces with whatever project you're interested in. You can build an IP and put that into whatever diagram you want. You can add it to whatever some larger HLS project. It's up to you, and it's fairly customizable. Okay, so let's see how this works sort of with an example. And so the example I'll use here is a jet classification example. I have jets that I make at the LHC, and they can come from from many different types of particles. So they can come from light quarks, heavy quarks, gluons, pile-up, heavy resonances, all sorts of things. And I'd like to distinguish these sorts of cases. And it's useful to mention that this is perhaps an unrealistic example for the level 1 trigger, but this is something that you could think about doing in the high-level trigger or beyond. And certainly the lessons that you learn by doing this are useful. This task is certainly a clear candidate for using machine learning. So what does this example network that we're going to create look like? So we use 16 sort of expert input features, and this is again why the classification is maybe not designed particularly well for level 1, but the conclusions are still valid. So I have some set of features here like the mass of the jet, some energy correlation functions, the multiplicity for the jet. And I pass it through 3 hidden layers with sizes 64, 32, 32. And then the final output is a 5-node softmax layer that distinguishes between the classes that you see here: light quark, gluon, WZ, and top. And if you count the number of weights, in this network here, you get something like 5,000, which is sort of on the upper edge of modern FPGAs. So the VU9P I showed would be able to fit this. Smaller FPGAs, more common ones, would not. And so, if I can't fit this network in my FPGA, I mentioned some other things that you can do, like the reuse to reduce the size, but there's also sort of training things that you can do in order to reduce the size of your network. And one of those is compression, which is basically just removing nodes or connections from your network. And to do this, we have a sort of a prescription to do this. We basically use a tool called L1 regularization, which adds a penalty term to the loss function of your network that basically penalizes it for having weights that are large. So you see the loss function sort of addition here. And what this does then is to sort of force the network to only use large weights if they really are needed to get the performance that you want. So in the plot on the left here, I have the relative weights if we just sort of train regularly without L1 regularization. And you can see that the weights, most of the weights are sort of all clumped together, and they're all sort of relatively large. And if we train with L1 regularization, you can move to the plot on the right, and you see that then you take some set of the weights that used to be large, and the network realizes that maybe it doesn't need to make these large in order to get most of the performance that you'd like. And so you end up with this sort of bimodal distribution here, where you have this sort of second class of weights that are significantly, orders of magnitude smaller than the other weights. And what we can do then is we can sort of prune these away, and so we can basically just chop out this second distribution here, and we're left then only with the weights that are really necessary. So we throw out, in this case, sort of the lowest 32% of the weights. And in fact, we can basically continue to do this forever. We have this pruned model. We can fix the weights that were removed to 0, and then we can retrain. And indeed, in this case, we can do this 7 times, and you can see that at the 7th iteration, we've basically reached sort of full pruning. There's a small amount of weights that have been pushed down to low values, but in general, we're not really getting too much gain out of more iterations. And so in this case, when we finally do the sort of last pruning, we find that we can remove 70% of the initial weights with essentially no impact in performance, which is really nice. And the other really nice thing is that HLS actually requires almost no sort of overhead to deal with these, because when it sees multiplications by 0, it knows to simply not wire them into the chip. And so we don't actually spend any resources doing 0 multiplications like you might on other architectures, which is really cool. So you can see here on the plot on the left, this is the DSP usage as a function of the precision. So the green curve here is sort of the full model with all the weights. The orange curve is the pruned model. You can see that after pruning, we basically, regardless of the precision, we get to remove about 70% of the weights, exactly like we expected. And then the plot on the right is the latency for the model. And here you can see a slight reduction at certain precisions. The other way to reduce the network size is to change the quantization. So this is connected closely to the default precision parameter that I talked about earlier. So the important thing to note here is that if I have weights that are very, very small, and I only have a certain number of bits to encode the fractional bit, anything less than 2 to the negative fractional number of bits basically gets automatically zeroed by quantizing the arithmetic and the weights that I store. And this then, obviously, if I have to take smaller bits to store the numbers, this means I have less resources needed to store the weights on the chip and less resources needed to actually do the multiplications. So you can see scans in these two plots of the integer precision and the fractional precision on the left and the right for the different classes that we output. And you can basically see that for integer precision greater than about 6, we have sort of full performance, and for fractional precision greater than about 14, we have full performance. Sorry, 8 as well. And so you basically you can do this scan yourself, but what you find is that at some point you don't need any more bits to get full performance out of the network. And so this is just another way to reduce the size of your network and help it fit on an FPGA. And indeed, you can use compression and quantization together. So in this case, the solid lines here are the full network, and the dashed lines are the pruned ones. And you can see that they all basically perform quite similarly, especially as you go to larger precisions. And so at some point, they both perform equivalently well and essentially at full performance. Okay, and then as I mentioned, the reuse is also something that you can tune to change the size. And I showed similar plots here. This is just a sort of a further scan of the reuse. So these are, again, the same plots, the DSP usage on the left and the latency usage on the right as a function of the precision. And then the different colors here are different reuse factors. And you can see that they basically scale as expected. So, the moving from the blue to the yellow means I add, I get to half the number of DSPs I use because I'm using them each twice. But it does mean that I take longer to do each of the computations, and that's true down the line as I increase the reuse. And so, as a sort of a concrete example of what you might want to do this for, in this case, you can see this dashed line here on the DSP plot is the number of DSPs on this particular device, a Kintex UltraScale. And obviously, if I wanted to use the full precision at the far right, it simply doesn't fit on the chip, but I can scan that down. And in this case, with our full performance, the 16.6 precision that I talked about earlier, we very, very comfortably fit in the chip. Okay, and then one final word, which is something useful to note when using a tool like HLS, is that all the plots that I've shown previously come from the HLS synthesis estimates, and there's pretty commonly known differences between the HLS estimates for resource usage and the final implementation. In general, the HLS estimates are conservative, and the final implementation will find ways to sort of get rid of or save resources in the final design. So we tested this for a slightly smaller model than I previously showed, so it's only 1 layer instead of 3. And we found that the flip-flops and LUTs are overestimated by factors 2 in some cases, in basically across the board, and the multipliers are fairly accurate. And so the multipliers are maybe the easiest thing to think about how it's encoded on the chip, and so that maybe makes sense why this is the most accurate. And also, this is another way that we can check that these designs are able to meet timing constraints, which are something that you have to consider when you're doing when you're using FPGAs. Okay, so I've tried to give sort of a very brief overview of the HLS4ML tool. I've obviously not gone through the full suite of capabilities, and indeed there's a whole range of things that we're constantly looking to add and improve on with the tool. So we have partial support for, I talked about DNNs mostly here, but we have already partial support for convolutional 1D and 2D layers. We have prototyping for LSTM and GRU layers, as well as graph neural networks. We have partial support for binary or ternary networks, and other things as well that I list here. We're also working, and we've made a lot of progress on the ability to handle large networks by making sort of full use of all the resources on the chip. And so I'd encourage you to sort of stay tuned for more updates and sort of an expansion of the kind of things that this tool covers. And what I'd like to talk about sort of in my later slides here is different potential use cases for this tool in LHC trigger systems, particularly CMS. So the first one that I'd like to talk about is actually sort of already in use and already being actively prototyped and sort of on track. So I mentioned before that the CMS NCAP muon trigger uses a BDT for the muon PT assignment. What it actually does is it encodes basically each possible output for the BDT given the inputs, and then encodes this in a very large DRAM bank that's on board the board that we use to implement this giant 1 gigabyte LUT basically to pick out the BDT output. And so there's work ongoing to actually replace this BDT with a DNN for the CMS Phase 2 upgrade. The development for this is being done with HLS4ML, and there's a talk there was a talk at CPAD 2018 if you'd like more information on this. One of the cool things about using a DNN as opposed to a BDT is that you can have multiple output nodes. So a BDT obviously has one output, and in this case, it's Q over PT for the muon. But in this case, we can actually simultaneously do the PT assignment and a pileup discrimination with essentially no cost to the size of the network, which is really cool. And obviously, this idea can be expanded even further. This particular implementation has already been found to fit comfortably within a VU9P and very comfortably within the latency budget of the level 1 trigger. So the algorithm latency for this particular 3-layer network that I show on the bottom right here is 72 nanoseconds, which is obviously quite quick, and it uses only 41% of the DSPs on a VU9P. So that's really cool that this is sort of already being used. There's also more preliminary work that's being done for the CMS trigger upgrade using HLS4ML for tau ID, as well as sort of other things like isolation and potentially other particle IDs as well. So that's maybe the obvious use case for HLS4ML. It's designed to produce things that you can produce designs that can be implemented on FPGAs, and we already use FPGAs in the level 1 trigger. But I'd like to argue that that's definitely not the extent of the tool's capabilities. So there's definitely an increasing popularity of these coprocessor systems, which is just a CPU connected to some sort of other architecture. Could be an FPGA, could be a GPU, TPU, what have you. The common setup for an FPGA is to connect it to the CPU through a PCI Express. And the gain or the benefit of having a coprocessor architecture is that you can basically allow your algorithms to run on whatever hardware they're most optimized for. So if I have inference and I think that that's more optimized for an FPGA than a CPU, I can send the inference to the FPGA, and I don't have to use the CPU to do the inference. And obviously that changes depending on what architecture you're talking about. One nice thing about, or one sort of convenient thing for us is that you can get access to FPGA CPU coprocessor machines on Amazon Web Services, AWS. So they have instances called F1 instances, and these are connected directly to a Vertex UltraScale Plus VU9P. And so we can actually use these, and we have used these, to sort of explore all sorts of possibilities for accelerating inference with HLS4ML. So sort of a brief word about how this works. Basically what's done is to develop sort of concurrently an FPGA kernel that you use to program the FPGA and CPU host code. And there's software tools to do this and to help you out that are already on the instances, but you can obviously get them locally yourself. The tool in this case is called SDAccel. But it basically uses Vivado HLS sort of under its hood. It makes the same sort of outputs that you'd expect from HLS, same sort of reports, things like that. So if you've already used HLS, it's sort of a very easy sort of switch and move to use SDAccel. And basically then what happens is if you look at the diagram on the right is basically I have some CPU host code that's running. It gets some set of inputs. It can transfer these back and forth between the FPGA kernel over the PCI Express, and then when it's done, it does whatever post-processing it needs to do when it's gathered the outputs from the FPGA, and it hands them off to you. And to use HLS4ML in this sort of paradigm, you basically only need to wrap it in certain specific I/O requirements that SDAccel has to make the kind of kernel it wants to make to put on the FPGA. But you can do this fairly generically for HLS4ML projects, which is really nice. And this means that we've accelerated all sorts of HLS4ML projects on F1s. The only thing really that you're limited in speed by is the I/O bandwidth of the PCI Express back and forth between the FPGA. Okay, so let's see how this actually looks in detail, and a case study that we've actually been very excited about. So HCal reconstruction at CMS currently uses an algorithm that's basically an iterative fit to determine the in-time energy of a signal. So the plot on the bottom left here, I have each TS time slice is 25 nanosecond bins, and I have some in-time signal in blue that's maybe been sort of clouded out by out-of-time signals in red and green. And so what I'd like to do is come up with some algorithm that basically returns to me the energy in that blue pulse and picks out the red and the green ones. So the current algorithm is sort of an advanced template fit where it has templates for each of the pulse shapes in each of the bins and does a fit in an attempt to extract this. This is obviously this is not a fast algorithm. So at HLT, the HCal reconstruction takes about 15% of the total HLT processing time. A similar procedure is used in the eCal reconstruction, and this takes 10%. So you can see that sort of local calorimeter reconstruction in the HLT takes about 25% of the processing time. And indeed, the situation is only expected to sort of get worse as we move to HL/LHC conditions with high pileup and things like that. And so what we've begun to do is look at whether we could use machine learning and whether we could use HLS4ML to sort of offer an alternative to this. And so what we did was to use similar inputs to the current algorithm. So we basically just use the sort of 8 time slice energies that we have, as well as information about which HCal or calorimeter cell we're talking about. So we have the position in eta phi and the depth encoded as well. And what we find is that with a fairly simple 3-layer network, so we have 11 inputs, we have 3 hidden layers with 15, 10, and 5 nodes. This is a very, very small network. We can get comparable performance to the iterative fit algorithm, even with this small network. And indeed, we have successfully implemented this and run the inference on AWS with the SDAccel tool. You can see sort of a prototype here of how the sort of data transfer and data handling works inside CMSSW. Maybe the main thing to note is that including the data transfer to and from the CPU, the whole FPGA inference process takes about 2 milliseconds for all 16,000 HCal channels. The inference alone takes 80 microseconds. Obviously, the data I/O, as I mentioned, is the main limiting factor here. And this has been tested, as I mentioned, inside CMSSW, basically using a standard HLT job to do this test. So every event basically computes or gathers the input energies that it needs to send to the inference, to the model, sends them to the FPGA, and then simply waits for a callback with the output node. In comparison, the iterative fit procedure on the same set of data takes about 50 milliseconds. So this is a factor of 25 slower. The other maybe nice thing about this is that the FPGA inference is a fixed latency procedure. So regardless of the the type of data that we're looking at, whether it's high pileup, low pileup, what have you, the FPGA will always take the same amount of time. Whereas the fit is not. That's not true for the fit. This is obviously a case for the FPGA being the optimal architecture to do the inference on. You can indeed look at how fast this same sort of procedure, this same model would take on a CPU or GPU, and you get numbers of about 15 and 12 milliseconds. So this is still significantly faster than the iterative fit, but the FPGA inference is still notably faster than all of these alternatives. Another thing that I'd like to mention as sort of a cool thing is that last week I helped to organize a workshop for both HLS4ML and this sort of this coprocessor acceleration. So the title was How to Do Fast DNN Inference on FPGAs. This was held at the University of Zurich. You can take a look at the Indico page there. There was a ton of interest, which was quite surprising, I think. So we had about 90 participants, which was really cool. And by the end of the course, everybody at the course was actually able to run their inference on an FPGA. So we used AWS. They all had an F1 that they could use. Which was really exciting, and we're interested in replicating this workshop at other locations because of the interest that we got. I won't go through the whole workshop program in detail here. Suffice it to say that we basically covered the sort of stuff that I've talked about in this talk. We sort of went through how to use HLS4ML. We went through how to use SDAccel. We went through how to do model compression and quantization, and then we went through how to actually run on an FPGA. Okay, and the final thing I'd like to mention is actually not maybe directly HLS4ML, but it's still something that I think is really exciting. So I've talked about sort of the rise of coprocessors, and indeed Microsoft has a CPU FPGA server farm called Brainwave that they have. And what they do is they offer machine learning as what's sort of quote unquote as a service. And what this basically means is that you send a preprocessed image to Brainwave, and you get some prediction back from ResNet 50. So the ResNet model runs on the FPGAs on the cluster, and you simply get the output. Obviously, you're sending data back and forth between you and a cluster, in this case in Virginia, I believe. So the latencies here are not microseconds, but this is something that I think is a really interesting option for longer latency tasks. The speed of light transfer is 10 milliseconds, so you can get some idea of the the latencies that we're talking about. And I'd encourage you to stay tuned for another talk. I won't be able to talk about this in detail, but I think we'll have another talk, hopefully in the future, on this sort of more completely. Okay, so I hope that you've been convinced, or you have seen today that machine learning is sort of becoming very, very widely used for all sorts of problems in physics, in industry, all over the place, and that indeed some of the more challenging problems in HEP definitely exist in the trigger system with these sort of latency constraints that we have to deal with. And that even if I have a machine learning solution for some problem in the trigger, I still need a way to implement that and to do the inference fast, and that basically points directly to using FPGAs. And that HLS4ML really does provide a really great ability to implement these with low latency, to customize them and to tune them exactly for the sort of resource usage, latency, accuracy that you need for your particular task. and indeed, we've already started to use this. So we've already used it to, or started to use it for the mu1PT assignment task that I talked about, for doing tau ID or isolation or other things like that in the level 1 trigger. But indeed, these improvements are not limited exclusively to level 1 trigger or to conventional FPGA systems. So, I gave you this example of the HCal reconstruction that we've demonstrated could see a pretty incredible speed up if you ran this sort of thing on an FPGA. You could envision having accelerator cards in the HLT and using these to do inference depending on inference on each of the nodes. And indeed, the HCal implementation is sort of just one case. Any sort of slow traditional algorithm that you can think of at the HLT may have a machine learning sort of alternative that we could run extremely quickly. And then I'd like to take the last second to sort of thank our full list of collaborators. I obviously won't go through everybody, but this list of all the institutes is rapidly growing, which is really exciting to see. Thank you.
Great, thanks. Are there questions? I know I have some, but I shouldn't ask my questions.
Yeah, I have a question on looking at how the number of multiplier units in the FPGA board affect the latency. It's essentially the number of weights between each consecutive layer of the neural network that's the real constraint, right? If my whole neural network has 8,000 weights and I only have 6,000 multiplier units, that's not the problem. If I have 8,000 weights between 2 layers, am I interpreting that correctly?
No, so it is indeed, at least if you're shooting for lowest latency and you don't store things in the block RAM, then indeed it is the total number of weights that are the limiting factor in terms of parallelization. Because in principle, what I'd like to do is I'd like to be able to pipeline these implementations with a clock cycle of 1. So I want to be able to send in a new set of inputs every single clock cycle, which means that I can't be using, if one layer takes the full set of DSPs, I can't use those to do successive layer calculations from inputs that I sent in earlier. Now this changes if you use the block RAM and you can offload or reload and offload things. But in principle, if you want a pipeline interval of 1, then this is how you limit it. Obviously, the reuse does change the pipeline interval. So as you change the reuse, the pipeline interval grows, and so that does affect how many DSPs you need to do the computations as well. Does that answer your question?
Thank you. Yeah, no, that's true. Thank you.
Hi, Dylan, this is David at Chicago. So first of all, thanks a lot. I have an overarching question, and I don't mean to bristle anybody, and sorry if it's a repeat of questions that Phil and Nan have heard before, but I wondered if, given this audience, it might be worth discussing. So my understanding is one of the biggest differences between or advantages or complementarities between HLS4ML and the entire suites of similar tools that both Xilinx and Intel provide is that perhaps you're providing maybe additional network architectures or perhaps some customization that is more appropriate for HEP applications. I wondered if could you go into how you see the differences between this and the ML suite and the Intel packages that also do pruning, compression, compilation, and synthesis for both Altera and Xilinx chips?
Yeah. So, I think that one of the biggest advantages to there's a couple, I think, huge advantages to HLS4ML. One of the biggest is that it's fully customizable, and what that really means is that we can use it to do extremely low latency tasks. And the the tools that industry develops, like the Xilinx ML suite and things like that, are really targeted at one very specific application, which is extremely large CNNs. That's basically what they do well. But indeed, even that, they do it fairly generically. So they basically implement systolic arrays, as I understand it, on the chip, which they can then be used to do whatever network you want. You just offload and onload the particular weights for the network. But in general, what you've really encoded there is just a set of large matrix multiplications. HLS4ML really does wire the exact network architecture onto the chip. And this means that you get extremely low latencies, even for larger networks, we're hoping, when you compare that to the ML suite. And indeed, we do expect that we should have, we will have, as you mentioned, we'll have larger or more coverage in terms of layer architectures and things like that. But I think the real advantage of HLS4ML is the customizability and the latency. That we can do these things significantly faster, or we have our implementations do them significantly faster than something like a Xilinx ML suite. I don't know.
That's it. Dylan, can I just say something real quick? Yeah, I think I'll just say that when we sought out to start thinking about these issues, I think the first thing that you notice, it's in one of Dylan's earlier slides, is that there's no industry tools for, let's say, tens of microseconds latency. They are primarily focused on coprocessors, sort of at the millisecond scale, and large network inferences. And right now it's convolutions, but it could be larger, or it could be others in the future. And so when Dylan started transitioning in the talk towards coprocessors and Brainwave and other things like that, there we are very conscious of what industry is doing and what's available and the tools that they're providing. But there's really nothing out there, especially if you're in an on-detector system. So you're not even. I mean, a lot of these setups from industry are specifically CPU connected to an FPGA system.
Okay. No, thanks a lot. I mean, you're right. That it does have an impact on the coprocessor discussion. So one of the things that you highlighted towards the end. Sorry, let me pull it back up to pull up the right page number. Was you don't have it in here, but I think you had it in your paper, if I recall correctly. So at some point, do you have the plot of the pruning and the network performance? Oh, sorry, it's on slide 25. Okay, great. So it's the dotted in the dash line where you discuss where you show that you basically don't get a difference in the physics performance, let's say, after the pruning. So here, how customizable is that? I mean, I don't recall seeing kind of a parametric discussion of the pruning aggressiveness and the area under the curve. Could you just mention how you benchmarked that, and what gave you the cutoff of 70% in this example, and going to other network architectures, how that would be accomplished?
Yeah, so this was done. I mean, this is not a fully scripted procedure, let's say. So this is something that you do depending on your particular model. In this case, we found that with 7 iterations, in this case, of the sort of the pruning procedure, that we could indeed keep essentially full accuracy, and with and its successive prunings would either require aggressive reduction in the weights, which would cost resources, would cost performance, or it would require, we would basically be pruning away one weight at a time, or some really small number, and that we were reaching the point of diminishing returns. So that's sort of how we went about deciding how many iterations and where the exact, maybe you're also referring to this sort of plot here where, we figure out where to cut the number of weights in the second distribution. Again, this is done sort of looking at where the separation is. This L1 really does seem to make these sort of bimodal distributions, and so it's easy to see in a lot of cases where exactly the sort of cutoff should be for the second pump.
Okay, so that answers the question. But so you see this, at least at the moment, being, let's say a scientific process as opposed to an automated process.
Yeah, David, I think we should say also that this is a Keras only, right? This is something you would do with your neural network, right? It's not an FPGA thing. I mean, you can add L1 regularization is kind of a standard tool in machine learning, and so you can add this and look at the distribution of the weights and vary your cut as you like it until to get the performance. So it really is like a user tool. It's not a feature of the FPGA. It's a user feature. And I mean, the fact that we can take advantage of this on the FPGA is a feature of the FPGA. But
Sure.
the printing itself is
can be done for anything. My point was that one might have to go significantly beyond what one would do in an offline, let's say, and network inference application. The whole point of you discussing this was to say that this is how one might get these things to even fit on the chip. And so my point, maybe to clarify, is given that, were you looking at, essentially a three-dimensional plot of network size, resource utilization, and performance, which is obviously tied directly to the FPGA. And it's a different goal than one has when one prunes a network for just some offline, non-latency restricted application, a non-resource restricted application. The point being that one might decide to buy a Vertex 7 or a Vertex UltraScale Plus, depending on whether you could prune away enough of a particular network and yet still get the performance you need and fit in one FPGA or the other. And that could save you tens of thousands of dollars. And if you're going to build hundreds of these things for a giant trigger system for phase 2, could save millions of dollars. I mean, that's the point, right? So that was the goal of the question, not.
Yeah, I mean, that makes complete sense. I mean,
so I had a question on, I think it was slide 33, that if I was worried about latency, I'd indeed rush out and buy an FPGA. But if I was worried about throughput per dollar, I'd buy a CPU. Are these, just to understand how to interpret these numbers, certainly the CPU must have been kept busy for the 15 milliseconds, but this sort of network, can you do better with a larger, with either pushing through more data or pushing through larger networks because you haven't kept the GPU or FPGA very busy? This sort of small network.
Yeah, so I should say the FPGA is fully busy when it's running. So it's this particular one is pipelined with an initiation interval of 1. So we send a new input in every clock for 16,000 clocks. The GPU in this case is actually running a slightly different network that's expanded to be even larger, so that you can pump even more data through it at once. But it's also batched by in this case it's a slightly smaller number, but you send the full set of 16,000 inputs in through the GPU network in this case all at once. And indeed we looked into, we did this to get the most out of the GPU for this case. But indeed you're right that this particular network is small. And so it's maybe not as targeted for a GPU as say a much larger network.
Is the same statement true for the FPGA case?
Not really in this. Again, the FPGA is being fully used I mean, the resources are fairly well consumed, and the chip is, I mean, the chip is running a new inference every single clock. So there's not a whole lot that can be done from the FPGA side for this inference to speed it up.
Okay, so it's essentially busy.
Well, but I think you should realize, right, the FPGA is only doing 80 microseconds worth of computing every 2 milliseconds. The rest of the time is transferring it on and off the FPGA. So it's not really that busy.
So how do you then get around that? How do you keep the FPGA busy? Or is the answer you can't in this case?
So
we have problems, where instead of 16,000 HCOT channels, you have 16,000, but then you have 1 million events. So there's plenty of, you can define very big data streams, but it doesn't sound like that's sufficient.
So let me ask, maybe I'll try to take a stab at this. This is actually something that we're studying, not directly in this context, but actually within this Brainwave thing that Dylan alluded to at the end here, where actually you could use one coprocessor to serve more than one CPU job, right? And that's what we're stress testing now, and so we're happy to come back and talk about this. But essentially, you could have, let's say 50 CPUs all pinging, one FPGA, and that way you would keep the FPGA busy the entire time.
Yeah, we're also, we're probably going to give an update on this at the HSF workshop that's coming up in a little more than a month. So stay tuned to that.
Okay, yeah, that was the kind of question I was wanting to understand. The bottleneck is because you're sending from one CPU, and if you have more, then you'd set up your network topology differently.
Right. Yeah. That is something that's optimized, and optimized also for your use case, whether you're HLT or offline computing or something else as well.
I mean, another thing we can do is just have the FPGA do more complicated computations, right? This neural network is tiny, so I mean, if it's doing a larger, more complicated computation, it will take longer, and the things will balance out more.
Okay. Anyone else with other questions? Okay. Let's thank Dylan, and I think we have another meeting on Monday for the people following the IRIS-HEP sessions. So thanks again, everyone, for joining.
Thanks. Bye.